Okay, today we will be talking about the cross product of two vectors. This is a very different sort of thing than the dot product. As you recall, in the dot product, we started with two vectors, and when we take the dot product of those two vectors, we get a number, a scalar. In fact, the dot product is sometimes called the scalar product for that reason. The cross product is very different. First of all, the cross product only applies to vectors in three-dimensional space. We don't talk about the cross product for two-dimensional vectors or four-dimensional vectors or anything like that. Second, the cross product of two vectors in three-dimensional space is another vector. It's a vector in three-dimensional space, so this is sometimes called a vector product for that reason. Anyway, I need to tell you how the cross product is defined, so let's start there. If V and W are two vectors in R3, that is three-dimensional space, then V cross W is the unique vector that satisfies a couple of conditions, three conditions actually, and I'll spell these out one at a time. The first condition is that V cross W is perpendicular to the two vectors V and W. So for example, in this case, given these two vectors V and W in space, V cross W definitely lies along this line that is perpendicular to both vectors. Now that constrains the possibilities somewhat, but not enough to specify V cross W uniquely. For example, it doesn't tell us whether V cross W lies in this direction or whether it lies in this direction. And once we know the direction, it doesn't tell us how long V cross W is either. That's where the next two conditions will come in. The second condition is that V cross W points in the direction given by the right-hand rule. Now what on earth does that mean? Imagine these two vectors right here, these are in space. Take your right hand and put the fingers of your right hand, not the thumb. Imagine that they're pointing along this direction, along vector V, the first one in the cross product, V cross W, so your right hand fingers are pointing in V. And now what you want to do is curl them around towards the other vector. So you curl them from V to W to figure out the direction of V cross W. When you do that, your thumb will be sticking up in vaguely this direction. The important point is that it is sticking up in this direction and not down here. The fact that your thumb, when you curl your fingers from V to W, is sticking in this general direction tells you which side of this line V cross W is going to lie on. It's going to be on this line and not on this one. But the question remains, what is the magnitude of V cross W going to be? How long is it? For various reasons, we define it so that V cross W is equal in magnitude to the area of the parallelogram determined by V and W. So let me write this down. Equal in magnitude to the area of the parallelogram determined by V and W. And with that definition, we really have specified V cross W uniquely. This parallelogram has a certain area, some certain number, and that number is precisely going to be the length of V cross W. So you just put up a vector like that, and let me clear out this mess, and we have it. This vector, whose direction is perpendicular to V and W, and moreover points in the specific direction given by the right-hand rule, and whose length is equal to the area of the parallelogram determined by V and W, that is V cross W. As we'll see, there will be many instances in which, when we're given two vectors, we will want to construct another vector that is perpendicular to both of them. The cross product is going to be our main tool for that once we have developed an algebraic way of actually computing the cross product of two vectors given the coordinates of those two vectors themselves. To check your understanding here, you might want to pause this for a second and see if you can figure out where W cross V would be located on this figure. Did you try it? Let's see if you were right. If we are looking for W cross V, that's going to be a vector that, first of all, is perpendicular to both of these vectors. So that means it's going to lie on this line. And then we have to think, well, what is the sense of it? Which direction is it generally pointing in? Is it pointing this way or is it pointing this way? Well, W cross V, if you put your right hand fingers along W and curl them around to get to V, you have to turn your hand over to do this. If you put your right hand here and try to curl your fingers through 270 degrees to get there, that's not going to work. You have to turn your right hand over, put the fingers along this, and then you'll see that when you curl your fingers towards V, your thumb will be sticking basically in this direction, which means that W cross V will be pointing in this direction. And how long is it? Well, it's going to be the exact same length as this one because its length will be equal to the area of that perpendicular. So I could just draw it on right here. It'll look something like that. It may not be exactly equal, but it's as close as I'm going to get by freehanding this. I hope you noticed the implication here for the algebra of the cross product. We've just shown that V cross W is not equal to W cross V. That means the cross product is not commutative. In fact, the cross product is non-commutative in a particularly interesting way. What we see is that V cross W is not only not equal to W cross V, but it is equal to the opposite of W cross V. We sometimes say that the cross product is anti-commutative because of this particular property. When you reverse the order of the two terms, you pick up a negative sign. This anti-commutativity of the cross product is the first of many interesting properties, which we will now develop. The second important property of the cross product we will discuss has to do with the special vectors I hat, j hat, and k hat. We want to know what happens when we cross one of them with another one. For example, what happens if we look at I hat cross j hat? Well, the result of I hat cross j hat is going to be perpendicular to both vectors, so it will lie along the z-axis. It's going to be given by the right-hand rule, so we curl our right fingers around from I hat to j hat, and we find that the result will be along the positive z-axis, and the magnitude of I hat cross j hat will be equal to the area of this parallelogram, and that area is of course 1, which means that the magnitude will be 1, which means that the vector we're looking at, I hat cross j hat, will in fact be k hat. Well, that's pleasant enough, and you can verify on your own that if you looked at j hat cross k hat, you will end up with I hat. And similarly, if we were to look at k hat cross I hat, we could reason out geometrically that this would be j hat. And what if we reverse the order of those? Like instead of I hat cross j hat, what if we had looked at j hat cross I hat? Well, you could reason that out geometrically, appealing to the definition of the cross product, or you could just use the anticommutativity property. You already know that I hat cross j hat is k hat, so by anticommutativity, j hat cross I hat must be minus k hat. And of course, you could do the same thing to come up with k hat cross j hat and I hat cross k hat. They're just the opposite of what we found already. This gives us a full multiplication table, as it were, of any two distinct basis vectors, I hat, j hat, or k hat, and you can actually summarize this in a very simple picture. This right here gives us that full multiplication table if you know how to read it. If we wanted, say, I hat cross j hat, if we wanted to read this off the table, well, we would say I hat cross j hat, going in this direction, brings us to k hat, which agrees with what we had right here. Similarly, if we wanted to know, say, k cross I, well, that goes k cross I takes us to j, which is what we saw right here. The other thing to bear in mind with this little diagram is that if we go against the grain, against the direction of the arrows, then we're going to pick up a negative. So for example, if we did j cross I, we're going against the direction of the arrows, that would bring us to k, but we're going to make it a negative k because we're going against the arrows. So j cross I would be minus k, which of course is what we had right here. And similarly, I cross k would be minus j, which we found already up here. So just by remembering this little diagram, you have the multiplication table for cross products of I hat, j hat, and k hat. We will need this in a bit when we derive a formula for the cross product in general of any two vectors in R3. We didn't, however, say anything about what happens if you cross one of I hat, j hat, and k hat with itself. Like suppose we looked at, say, I hat cross I hat. What would that be? Well, its length would be the magnitude of the parallelogram spanned by I and I. But there is no such parallelogram. That means its magnitude would be 0. which means the only vector this could possibly be, the only vector with 0 magnitude, is the 0 vector itself. And similarly, of course, j hat cross j hat is the 0 vector, and k hat cross k hat is the 0 vector. And in fact, any vector whatsoever crossed with itself will give you the 0 vector. And that is something worth bearing in mind. You can work it out from first principles anytime you need it, but it's good to know that when you cross any vector with itself, you get the 0 vector. This is a special result. It's kind of like when you dot any vector with itself, you get the square of its length. Crossing a vector with itself gives you something spectacularly simple. Okay, in the last video, when we were talking about the dot product, we discussed how if we have a pair of vectors v and w, the dot product of those two vectors is the length of v times the length of w times the cosine of the angle between them. Well, there's something similar we can say about the length of the cross product. Now, the cross product is a vector, unlike the dot product, which is just a scalar. But the cross product has a length, and its length is given by a particularly simple formula. So let's think about that a little bit. If we were thinking about just the length of the cross product of two vectors, we're going to come up with a formula for that, and we want it to be in terms of the length of v, the length of w, and this angle between them. Well, when we do that, we have to think about this parallelogram, because its area is going to be the length of v cross w. Well, what is its area? That's easy enough to find. The area of a parallelogram is just its base times its height, because we could take one triangle here, chop it off, and reattach it here, and so we would just have a rectangle. So we want to come up with an expression for the height of this thing. Well, that's easy enough. We drop a perpendicular here to get the height, and so by ordinary trigonometry, this is just the length of w times the sine of theta. And since this is, of course, the length of v, we have that the length of v cross w, which is the area of that parallelogram, is going to be its base, which is the length of v, times its height, which is the length of w, times sine of theta, where theta is the angle between v and w. And so here we have the famous formula. So if we've been given two vectors, v and w, we can determine the length, at least, the magnitude of their cross product by taking the product of the lengths of the two vectors and multiplying by the sine of their included angle. This is a formula that is well worth knowing. We will eventually come up with a formula for the cross product in terms of the components of the two vectors involved. But before we do that, we need to develop some basic algebraic properties upon which that derivation will be built. The first such property is an associative type property. It looks exactly like the one we did for the dot product, except it involves the cross product. If we have alpha v cross w, well, we can just pull that alpha straight out of the cross product so that we have alpha times v cross w. Anyway, let's explain why this particular associative property holds. Here I have drawn all the vectors that are involved in this formula. I have w, I have v, and then I have a scaled version of v, alpha v. Now, to show that this formula holds, we have to show that the two sides, both of which represent vectors, are in fact the same vector. In other words, we have to show that these two vectors point in the same direction and have the same length. If that's the case, then they represent the same vector. The first part is obvious. They clearly point in the same direction. If we look at the first vector, alpha v cross w, that's this green vector crossed with w. Well, we know it's going to be perpendicular to them both and is going to be, in this case, pointing in this direction by the right-hand rule. On the other hand, alpha times v cross w, well, here's v cross w. Still, it's going to be pointing in the same direction, and all alpha does is scale it, so it'll just be a little bigger. So these two vectors definitely point in the same direction. The only question is whether they have equal magnitudes. Well, the magnitude of the expression on the left-hand side, alpha v cross w, that, of course, is just going to be the area of this parallelogram. On the other hand, the length of this expression on the right-hand side, that will be alpha times the area of this purple parallelogram. But alpha times the area of the purple parallelogram is in fact the area of the blue parallelogram. I will leave it to you to convince yourself of that simple geometric fact. And so we have shown that these two vectors are in fact the same vector, which means that we can take a constant and pull it out through the cross product. As with the dot product, it is also true with the cross product that you can pull a scalar out through the second position like that. I'll leave that as a small and pleasant exercise for you to do. You don't need to do this one geometrically. You can just do some basic algebra using the property we've already used and the anticommutativity property to prove that this is true as well. What about distribution? What if we have something like this, where we take V and cross it with a vector sum? Are we allowed to distribute the cross over this vector addition? We can do it. Proving that this holds, based only on what we've proved so far, is not easy. It can be done, but the proof is pretty elaborate to drop into the middle of a video like this. So I'm going to ask you to take this for granted, or don't take it for granted. Accept it that it is true, but you should leave a little flag in your mind there, wondering why this is true. Maybe you can try to prove it on your own and see if you can come up with it. It isn't an easy proof. Okay, taking the distributivity as read, we turn to something that I have mentioned a few times already. If I have two vectors given by their components, like I have vector A, whose components are A1, A2, A3, and vector B, whose components are B1, B2, and B3, then if I want to find the cross product, A cross B, what will the components look like? We have developed enough tools at this point that we can find this formula without too much trouble. However, it will turn out to be a little bit nasty, unlike in the case of the dot product of these two vectors. Fortunately, we will find a simple mnemonic device that will render it easy to remember. Okay, let's get to the derivation. We'll begin by expanding A and B in terms of their I hat, J hat, and K hat coordinates like this. Now, as I mentioned, you can distribute the cross over vector addition. So we could think of this whole thing as one block and distribute it to these three terms. Once we did that, we would have to do some more distribution, and once all the distribution settles, we will end up with the usual sort of thing from elementary algebra, where every term in this group gets crossed with every term in this group, and then we add them all together. And the result will look like this. Ugly, isn't it? We can clean it up a little bit, though. And the first thing we'll do to clean it up is to pull these constants out. In each cross product, we have 9 different cross products now. But in each one, I can pull this constant out, and I can pull this constant out. So for example, in the first of those 9 terms, I can rewrite that by pulling the scalars out, A1, B1, and I'm left with I cross I. And if I do that for all 9 terms, we end up with this, which isn't nearly so bad, because now we see that in each term, we have something like I cross J, I cross K, and we know all about those things already. In particular, we know that if you cross anything with itself, you get the 0 vector. That means I can effectively cancel out this term, and this term, and this term. As for the remaining 6 terms, we can simplify all of those using this multiplication table that we discovered earlier. So for example, in this first surviving term here, A1B2 times I cross J. Well, what's I cross J? Well, we look over here. I cross J, we're going in this direction. I cross J, so that gives us K. So that first term actually is just going to become A1B2 times K hat. And let's do one more of those. If we move to the next one, A1B3 times I cross K. Well, what's I cross K? We're going against the grain in this particular example. I cross K, that means we're going to get a negative J. So that means that next term becomes A1B3 times negative J. So why don't I just turn that into a minus J hat? And when I do the same for the remaining 4 terms, we end up with this. We have 6 terms. 3 of them are subtracted. The other 3 are added. And we have I occurring in 2 places, once added and once subtracted. J occurring in 2 places, once added and once subtracted. and k occurring in two places, once added and once subtracted. We can simplify this a little more by combining the I hat, j hat, and k hat terms, respectively. When we do so, we end up with this. And in one sense, we are done. I have a fairly simple formula. It may not look simple, but a fairly simple formula for the cross product in terms of the components of the original two vectors. We have an I hat component and a j hat component and a k hat component. And there are nice patterns here as well that you might pick up on if you stare at it for a little while. But the first thing I want to do is to clean it up a little bit more by using shorthand notation to condense it a bit. And this will look even better if we clear out some of the clutter. That's looking better already. Now what I want to do is show you a kind of mnemonic device that you can use to recover this so that you don't actually have to memorize that awful thing. It's basically a notational device, and it works like this. If we're given our two vectors in R3, A and B, we're going to write them in an array like this. Between these vertical bars, we're going to put a row in the middle that is the components of A, that's vector A, and then we're going to put a row at the bottom that is the components of vector B. Upstairs in the top row, we're going to write I hat, j hat, and k hat. And this weird array is just going to be our symbol for a strange kind of computation that we'll do. What we're going to do, I'll try to say it a few different times. I'll do it first abstractly, and then we'll do some concrete examples as well. We're going to start up here with I hat, and we're going to multiply the thing. We're going to start at I hat, and we're going to go down to the right, and we're going to multiply those three things together. And when we do that, of course, we would get A2, B3, I hat. Then what we want to do is go, starting at I hat again, taking a diagonal to down and the left. You say, well, how the hell can you go down to the left? You run off of this array. Well, it's kind of like a 80s video game. You go off the screen here and you come back on the screen right here. So Pac-Man leaves here and he comes right back in here. So if we're going diagonally this way, we would have I times A3 and B2. And whenever we go left, we're going to pick up a negative sign. So we would get negative I A3 B2 like that. So we're going to get a couple of I terms this way. We're going to get A2 B3 I. And we're also going to get, when we go the opposite direction, A3 B2 minus I. So when I put those together, I end up with A2 B3 I minus A3 B2 I, which of course we could combine into one term like this. And notice that what I have right here, A2 B3 minus A3 B2, that's exactly what I had right here. So this is good. Now, I'm not quite done. Maybe I shouldn't have even written that equal sign yet, because there are two more terms to come, and I'll bet you can guess what they are. What we did with I, adding down this diagonal and then subtracting the products along that diagonal, we're now going to do with j. So if we throw in j, let's see, we're going to get first the plus one. We're going to get j, and the scalar we're going to multiply by will be A3 B1. Once again, we're going off the screen here, so we come back here. A3 B1. So I'll go ahead and write that in, plus A3 B1 j, and then we have to go the other way and get a negative. From the j hat here, we're going to get A1, and then we come back on the screen here, B3. So we would get a minus A1 B3 j hat. And of course, I can combine these two terms and simplify it a little bit if I do this. Good, and once again, this matches what I have up here. Well, I don't think I need to tell you what you're going to do for the third term. You're going to do the exact same thing with k. And let's see if we can just do that all at once. If we do it with k, we're going to get, when we go down and to the right, we immediately run off the screen, so we get A1, B2. So I'm going to go ahead and write down A1, B2, and then when we go to the left, A2, B1, which is going to be subtracted. So A2, B1, K. And lo and behold, this agrees with that. So what we have here, this strange little notational convention, that actually gives us A cross B. And in practice, whenever you have to actually compute a cross product, this is what you do. You write down A cross B is equal to this strange thing, and then you just churn it out. And after a while, you probably don't even write the I-hats, J-hats, and K-hats. You just write it in shorthand notation all in one shot. So let's do a concrete example with numbers to see how it works. Let's say we have these two vectors in R3, namely 2, 0, 1, and minus 1, 1, 3. You could try to draw them on a graph. I'm not going to bother, but they're two vectors in space, and we're looking for their cross product. So we're looking for a vector that is perpendicular to both of them, and its direction is given by the right-hand rule, and its length will be the area of the parallelogram that they span. Now, miraculously, by everything we've developed so far, maybe it's not that miraculously, we can do this with just a couple of quick computations, very mechanical. So to set everything up, what are we going to do? Our solution, we set this funny array up where we have I-hat, J-hat, and K-hat on top. And then we have the first vector, 2, 0, 1. It's important that we keep the order straight. Minus 1, 1, and 3. And now we just have to crank this out the way I explained a moment ago. Let's just see if we can write it down all at once in shorthand notation. I think you won't find this any trouble at all. So for the I-hat term, the thing that goes in the first component, we're going to get, let's see, we multiply these, and we're going to get 0 right there. Okay, so we get a 0 there, but of course we're also doing the negative version, and we'll get a 1 there. So we get 0 I-hat minus 1 I-hat, which means that first component is just going to be a minus 1. And now when we move on to the second component, our J-hat stuff, we start at J-hat and we go down and to the right, and we're going to get 1 times minus 1. So we're going to get a minus 1, and then we have to subtract from that. 2 times 3 is 6. So we get that minus 1 minus 6, which of course is minus 7. So that's going to be our second component. And finally, the third component, we have K-hat. So let's see, starting here, we go down and to the right, which takes us immediately over here. We have 2 times 1, that's going to give us 2, and we're subtracting off nothing because of that 0. So we get plus 2 minus 0 is good old positive 2. And look at that, all at once, without drawing a picture, without doing anything, we have found the cross product of our two vectors. This vector, we know, is perpendicular to both of those. We could check that very easily by, say, taking the dot product with either of them, and we should get 0 when we do that. It follows the right-hand rule. If we curled our fingers around on the right hand from this one towards this one, our thumb would be sticking in the direction of this cross product. And the length of this cross product, which we know how to find, is going to be exactly equal to the area of the parallelogram spanned by those two vectors. So this is nice. We've really packed a lot into this thing right here. To reinforce what we've done here, let's do a simple geometry problem. Okay, here's our problem. Find the area of a triangle whose vertices are given by these 3 points, A, B, and C. Now I've sketched out this rough picture of what's going on. You could solve this problem entirely by trigonometry. It would be a bit of a pain, but it's a lot more fun to do this problem using vectors and the cross product. So let me show you how we might do that. The first hint that we might use vectors and the cross product here is just the fact that the area of a triangle is exactly half the area of a certain parallelogram. And we know that the areas of parallelograms are related to lengths of cross products. In fact, if I were to find the cross product of those two vectors, its length would be the area of this parallelogram. And then all I'd have to do is cut that in half and I'd have the area of my triangle. Nice, isn't it? Very simple conceptually. All we have to do is carry out the computations. So our first observation is just to put in writing what I just said a moment ago. The area of the triangle we want is half the area of this parallelogram. The area of that parallelogram is the length of a certain cross product. Namely, it's going to be the length of vector AB crossed with vector AC. Naturally, to compute that cross product, we're going to need, first of all, to get the components of these two vectors. Well, that's pretty easy. Let's start with AB. So AB is this vector right here. we're going from 1, 1, 2 to 3, 1, 3. So I just have to think, all right, if I'm starting at point 1, 1, 2, what vector do I have to add on to get to 3, 1, 3? From 1, I have to add on another 2. So the first component here is going to be 2. From 1, the second component, I stay the same. I don't have to add on anything. So the second component is going to be 0. And from 2, I have to add on 1 to get up to 3. So I get 1. And now I want to do the exact same thing with vector AC. That entails subtracting 1 from the first component, adding 1 to the second component, and adding 3 to the third component. So our vector will be -1, 1, 3. Thus, I can now compute the actual cross product we're looking for. 2, 0, 1 goes here, the first one, and then -1, 1, 3. And we'll crank it out, and maybe you can even already do it in your head. Let's see. First component has to do with I. We go down and to the right, we get nothing. And then when we go down and to the left, we get 1. So we have to subtract off 1. So we get a -1 there. As for J, let's see. We're going to get, when we go this way, 1 times -1 is -1. But then from that -1, we have to subtract 6. So that's going to give us -1 minus 6 is -7. And then we have K, which is going to give us 2 minus 0. So we're going to get a 2 right there. So we have the area of the triangle is half the length of that vector. And the length of a vector is something we have known how to compute for a long time. Let's see, we're going to get the square root of the sum of the squares of the components. So that's 1 plus 49 plus 4. That's 54. And if you want to make your 8th grade teacher happy, you note that this has a square factor of 9. So you can pull out a 3, and that leaves you with, what is that, 6?